after studying this module, you shall be able to know what is anchimeric assistance, learn the mechanism of anchimeric assistance, identify the functional groups which take part in anchimeric assistance, and you shall be able to evaluate the outcomes of anchimeric assistance for various reactions. And after going through all these details, you shall be able to know how to analyze if anchimeric assistance is operational or not. When a catalytic functional group or atom is part of the reacting molecule, and if that is aiding in catalysis, that is, this type of catalysis is called intramolecular catalysis. Anchimeric assistance, if you look at this term, anchimeric in Greek means adjacent parts, and in case of intramolecular catalysis, where a suitably placed intramolecular nucleophile assists in a substitution reaction by enhancing the rate of reaction, is called as anchimeric assistance. Let us try to understand the mechanism of anchimeric assistance. The bimolecular mechanisms for nucleophilic substitution, as you are already aware, are termed as SN2 reactions. The SN2 reactions, you are already aware, they follow second order rate kinetics. The geometric alignment of transition state for SN2 mechanism is such that the nucleophile attacks from the backside of that of the leaving group from which it is getting lost, and this leads to the inversion in configuration. However, there are some examples of retention of configuration in SN2 reactions, where an atom or group close to the carbon undergoing substitution assists in the reaction with its available pair of electrons, and such a group is called as a neighbouring group, and the assistance provided is termed as neighbouring group participation. If such participation leads to an enhanced reaction rate, the group is said to provide the anchimeric assistance. As you can see here, in step 1, this particular group Z is attacking on this carbon further attached to X, and as the X minus goes, it leads to the formation of these 3 membered cyclic intermediate, and here notice that the Z group is what is the neighbouring group which has participated in this mechanism and helping in the anchimeric assistance. Once this 3 membered transition state is formed, in the next step what happens is the attacking nucleophile, say Y minus, will be attacking, and Z as a result goes back to in its position. So, this mechanism for anchimeric assistance is a 2-step mechanism where 2 conjugative SN2 reaction leads to retention of configuration. So, if you look at these 2 steps, you can clearly see the configuration is being retained. It is not the backside attack, unlike the simple SN2 mechanism. In the first step, the neighbouring group Z acts as a nucleophile attacking the substitution center and expelling out the leaving group, and in the next step the external nucleophile Y attacks from the backside, displacing the neighbouring group and retaining the overall configuration. Since the first step is slow and is rate determining, the reaction follows the first order kinetics and there is no effect of concentration of Y minus on the rate of reaction. Anchimeric assistance enhances the rate of reactions by several order of magnitudes, and this is because the step 1 being the rate determining step and neighbouring group Z, which is readily available within the substrate, makes the attack much faster as compared to attack by an external nucleophile Y, for which to react the substrate has to collide with Y minus. Since Z is readily available by virtue of its position, its attack is much faster. Thermodynamically also, Anchimeric assistance is favored as the reaction between the substrate and Y- involves a large decrease in entropy of activation, as the reactants are far less free in the transition state than they were before. Reaction of Z involves a much smaller loss of entropy. And if you look in terms of atoms and groups which can act as neighboring groups, they are COO minus, COOR, COAR, OCOR, OR, the OH, O minus, NH2, NHR, NR2, NHCOR, SH, SR, S minus, SO2PH, I, Br and Cl. The effectiveness of halogens as neighboring groups decreases in the order I is maximum, followed by Br, then followed by Cl. The chloride is a very weak neighboring group and can be shown to act in this way only when the solvent does not interfere. Now, after understanding the basics and the mechanism how the anchimeric assistance takes place, let us consider some examples of reactions where anchimeric assistance is operative. NGP, that is the neighboring group participation, takes place by internal attack of a nucleophile leading to the formation of a ring. Upon the attack of external nucleophile, the ring can have three different fates, that is either the ring opening at the same point where the ring closure took place, that happens, or ring opening at a different point from which the ring closure took place, or we can have no ring opening so that the overall reaction is a cyclization. So, let us consider these three one by one. So, first of all, the case where ring opening happens at the same point where the ring closure has taken place. That is, you can see in this particular example here that this OCOCH3 is providing the neighboring group participation or the anchimeric assistance, and then this double bond of the OCOCH3 will be via the oxygen will be attacking on this carbon which is further attached to Cl, and it helps in the removal of Cl minus group. So, once the Cl minus goes out, you can see this is the intermediate situation which is obtained, the carbocation, and this is further then attacked by OAC minus, which attacks at the same position where the Cl was there, and notice that the stereochemistry of Cl and the OAC which is attached is same, and as the OAC minus attacks here, this OCOCH3 will be brought back into its own position. Such reaction they lead to a non-rearranged product with the same configuration as the starting material. If you look at the second case is the ring opening at a different point from which the ring closure took place, and let us consider this example here. Here we have phenyl ring at this particular position, and further there is a OBS group which is a good leaving group, and this phenyl ring will assist in the removal of OBS, and as this OBS minus goes, there is the formation of this 3-membered cyclic intermediate, and you can see this positive charge is being accommodated by the phenyl ring conjugation, and this OAC minus will be further attacking, but the attack is now happening at the other carbon, not at the initial carbon where OBS you can see was attached. So, not at this carbon, but at this tertiary carbon. So, at this tertiary carbon the attack happens, and this leads to the ring opening and giving you this particular product. So, you can see here in this case the position where the ring closure took place and the ring opening are at different points. So, these type of reaction they lead to a rearranged product, as you can clearly see from the starting one. It is not the OBS on which place the OAC is coming in substitution, rather the OAC is coming at the rearranged position. And looking at the third case are those where no ring opening happens, so that the overall reaction is a cyclization, and that can be seen from this particular example. Here you can see that this molecule having both NH2 and Br. So, NH2 group is providing the anchimeric assistance. It attacks on this carbon which is further attached to Br because of their cyclic position. It will lead to a 5-member cyclic next intermediate, and this NH2 attacks on this carbon, Br minus goes out, and what we get is this cyclized product. At times the cyclic intermediates may undergo ring opening at 2 points competitively, so that some of the product is rearranged and some remains unrearranged. The initial existence of the phenomena of anchimeric assistance was observed for the reaction where DL pair of 3-bromo-2-butanol when treated with HBr to give DL2,3-dibromobutane, where the erythro pair gave the mesoisomer, and this we can see here as shown, that if we start with 3O, that is either D or L of this 3-bromo-2-butanol, and when any of these is treated with HBr, we are getting both the plus and the minus forms, that is you get this D plus L mixture of 2,3-dibromobutane. On the other hand, if you take this erythro, that is either D or L you start with, and when you do the reaction with HBr, we get the product meso in both the cases, that is D will also give meso and L will also give meso. Interestingly, either of the two 3O isomers alone also gave DL pair, and this is explained by the presence of a common bromonium ion intermediate formed as a result of attack by the neighbouring bromine atom. So, here in this case you can say that this particular bromine is acting as a neighbouring group, and as this Br will be attacking on this carbon, there is the removal of water molecule leading to the formation of this cyclic cation, where Br is bridged between these two carbons. And in this case there is an inversion at carbon 2 which is happening. So, this symmetrical intermediate gives equal opportunity to the incoming electrophile, which can either attack this carbon or this carbon equally. So, that is why when you start with the 3O, that is D or L, there will be formation of both plus and minus, but when you start with erythro D or L, then there will be formation of the meso product via these two possible attacks. Now, moving further, one question comes that how do we know if anchimeric assistance is involved in a reaction mechanism? Experimentally, to demonstrate the involvement of anchimeric assistance in a reaction, methods are to be employed. That is, first is comparing the rate of neighbouring group participation with the rate expected in the absence of participation. The reaction where participation takes place, these reactions go much faster. To compare the rate constant for the intramolecular reaction with that of the analogous intermolecular one, and this method is limited to those systems where corresponding analogous intermolecular reactions may occur. Here the rate of intramolecular reactions is much faster as compared to intermolecular reactions, and Third is the examination of stereochemistry of the products which are formed. Unusual stereochemistry might be observed, such as retention of configuration, although going via SN2 mechanism. So, here reactions with rearranged products due to anchimeric assistance through a cyclic intermediate have been observed. The cyclic intermediate gives the external nucleophile with equal potential to attack any of the carbon atoms based on polar and steric conditions. The more stable product would predominate as shown here, and you can notice here that this Z is attacking on this carbon further attached to X as the leaving group. As a result, we get this cyclic intermediate as the cation, and Y minus can now attack on this carbon rather than attacking here, and it can attack here, and in this case you can see the rearranged product is there. And in such cases, substitution and rearrangement products are often formed together. So, all these are the indications that the anchimeric assistance is taking place. Let us consider the reactions with oxygen as the neighboring group donor and go into more details. The acetylysis of two different substrates, if we consider, that is first shown here as A 4-methoxy 1-pentyl brosylate and B, which is 5-methoxy 2-pentyl brosylate with a common intermediate structure, gave the same mixture of products which further confirmed participation by the neighboring group, leading to a common intermediate. And you can clearly see here, whether you start from this A or you start from this B, you are getting this particular intermediate from both of them. And what you can see in case of A, the OCH3 has attack on this carbon with the removal of OBS minus, given you this intermediate, and similarly here this OCH3 positioned at this place has attack on this carbon with the removal of OBS minus and given you this common same intermediate. And once we get this intermediate, it can lead to the attack further, that is OAC minus can attack either at this carbon leading to this particular product in 60% yield as shown here, or the OAC minus could attack on this carbon, thereby leading to this particular product which is formed in 40% yield. So, it is irrespective whether you start from A or B, that is either you start from 4-methoxy 1-pentyl brosylate or you start from 5-methoxy 2-pentyl brosylate. In both the cases we get these two products in this particular composition. The hydrolysis of 1,2-dichlorohydrin under alkaline condition was found to yield 1,2-diol with retention of configuration, although following SN2 mechanism. Here formation of a cyclic intermediate takes place as a result of anchimeric assistance, and you can see here. So, let us try to understand this as shown here. This chiral carbon, where you can see this Cl we want to replace by OH via hydrolysis, had it undergone SN2, the OH minus would have done the backside attack and led to the inversion in stereochemistry. But now what is happening due to anchimeric assistance, and the anchimeric assistance you can see in the presence of base, this OH will undergo deprotonation and give you O minus, and this O minus does a backside attack on the carbon and leading to the removal of Cl minus. So, there is a inversion which is happening at this stage, and we are calling this as inversion 1, and it leads to this 3-membered cyclic intermediate. Now, after this inversion has happened, the OH minus attacks as the nucleophile on this carbon and leads to ring opening again and formation of O minus. So, this OH when it attacks is again from the back side, and there is another inversion, and there is another inversion which we are referring as inversion 2 which is taking place. So, this inversion 2 is again leading to this particular product where effectively we have replaced Cl with OH, and further this O minus will take the proton from water and give you the OH back. So, now if you look at the overall route, there are two inversions happening. It is due to the anchimeric assistance of this OH group so positioned that two inversions is leading to overall retention in the configuration. Considering another example of anchimeric assistance in cyclic system with oxygen donor is this reaction, as you can see here, where one starting material has syn and the other has anti-stereochemistry. However, the products in both the cases have the same, that is anti-stereochemistry. Now, how that is happening you can see here. When we start with this anti-diastereomer, you can see this OTS and OAC are in the anti position, and when this is attacked with ACOH, the product formed is in place of OTS we get OAC, that is there is a retention which happens at this particular carbon. On the other hand, if we start with the syn diastereomer where OTS and OAC you can see are on the same side, and then when it is reacted with ACOH, the OTS is replaced with OAC and this reaction goes with inversion at this particular position. So, one reaction is going with retention and other is going with inversion. So, although the product obtained is same in both the cases, but it is noteworthy that in the earlier case in the where we have started with this anti-diastereomer, as you can see here, there is a anchimeric assistance, but when we start with syn diastereomer there is no anchimeric assistance, and that is why the later one where no anchimeric assistance, there is the inversion happening at via the SN2 mechanism, and in the when we start with this anti-diastereomer, then this OAC is helping in the anchimeric assistance and providing the formation of the product where the retention in configuration at the affected carbon is there. So, let us try to see its mechanism. The mechanism involves participation of acetyl group in the expulsion of tosyl group, as we can see here. So, shown here is first the conformation of this cyclic molecule where both the substituents OAC and OTS are equatorial, and due to ring flipping both will come to the axial position, and you can see this OCO CH3 group is so positioned that this O can attack on this carbon and lead to the removal of OTS, and then it leads to the symmetrical intermediate, and this is further resonance stabilized, you can see as shown here, and this will be then further attacked by OAC and leading to the retention of the stereochemistry via this anchimeric assistance. Thus, only when both the substituents are in axial position, there is a greater chance of anchimeric assistance and faster kinetics is observed. For the syn diastereomer, the neighboring group participation is impossible, and substitution goes simply by the intermolecular displacement of the OTS group by the OAC group. Therefore, just one SN2 step leads to overall inversion of configuration and is a considerable slower reaction as compared to the first one. Now, after the case of oxygen, let us look at the reactions where sulfur acts as the neighboring group donor. The hydrolysis of ETSCH2CH2Cl as shown here was found to be 10 raised power 4 times faster than the ETOCH2CH2Cl under comparable conditions owing to the sulfonium ion intermediate mediated anchimeric assistance as you can see here. So, what you can see here is this ETS group via the sulfur will be attacking on this carbon further attached to Cl and leads to this 3-membered intermediate, and further when water attacks, then it will be attacking on this carbon and moving these electrons back to sulfur. As a result, we have the formation of this product where the Cl has been replaced by OH, and in this case the sulfur has mediated and provided the anchimeric assistance. In comparison, for ETOCH2CH2Cl, that is in place of SET if we have OET, this substrate, the electronegative oxygen atom provides no internal assistance and thus the reaction proceeds with simple SN2 mechanism. For the substrates of the type RS with CH2CH2X, the neighboring group participation occurs so readily that ordinary SN2 reactions are hard to observe. Trans 2-thiosubstituted chlorocyclohexane undergoes reaction with aqueous solution of ethanol almost 70,000 times faster than the unsubstituted compound. However, the corresponding cis 2-thiosubstituted compound, they react a little more slowly than the unsubstituted compound. These experimental observations have been ascribed to anchimeric assistance provided by sulfur atom present in the correct stereochemistry to assist the expulsion of the leaving group. And you can see here that with this particular conformation, the SPH group and the Cl, they are both axial and are positioned anti to each other. So, in the trans geometry, when this sulfur can easily attack on this carbon, helping the expulsion of Cl group and provides the anchimeric assistant via the formation of this 3-membered intermediate. And this 3-membered intermediate, the water will have only this way to attack, which is anti to the positioning of SPH, and then as the water attacks here, the SPH goes back to its original position and this OH2 plus further undergoes deprotonation and gives you this OH in place of Cl. So, what you can see is, as compared to the starting molecule, the resulting product has the perfect retention in the stereochemistry. So, as shown here, the thio substituent displaces the chloro group by attacking the back side of the carbon to which the chloro group is attached. Since the backside attacks require both substituents to be in axial position, thus only the trans isomer which has both of its substituent in axial position react faster. Subsequent attack by water or ethanol on the sulfonium ion is further facilitated as the positively charged sulfur is an excellent leaving group and breaking the 3-member ring releases the angular strain. Let us now continue further by taking the reactions where the nitrogen acts as neighboring group donor. Amines as lone pair donor for anchimeric assistance can be seen in this particular example. You can clearly see here the lone pair over the nitrogen attacks on this carbon further attached to Cl as the leaving group. So, as this attacks here, the Cl can go out and leading to this intermediate cation, which further by attack of OH minus will be giving you this particular product. But here look at, there is a rearranged product which has been formed. So, in this reaction the substrate is a secondary alkyl chloride and the product obtained is a rearranged one, which is the primary alcohol. Let us consider some more examples, and in this example as being shown here, the N-Me2 group is providing Anchimeric assistance for the hydrolysis of ester. So, you can see here the ester is the COOPH group, and this N through the lone pair from this NME2 group will be attacking at this carbonyl carbon of the ester group and forming this intermediate oxyanion. Eventually it will make the OPH go out and give you this CO with N, and this followed by hydrolysis, the water will attack at the carbonyl carbon and give you COOH, and the NME2 is brought back to its original position. So, you can see here in this particular case the NME2 has provided Anchimeric assistance for the hydrolysis of this COOPH group, which has got converted into COOH, and obviously the phenol will be the byproduct. A ring expansion reaction involving Anchimeric assistance can occur as shown here. So, you can clearly see here we are starting with this 5-membered cyclic ring having nitrogen, and nitrogen through the lone pair will attack on this carbon, further attached to Cl, which is a good leaving group here, and so as this attack happens it will lead to this 3-membered intermediate as the additional ring, which is further joined to this 5-membered ring. But this 5-membered ring and 3-membered ring, this is quite instability. So, further what happens is as the Cl minus attacks here, rather than opening back in the same way, it will be this NC bond which will go into cleavage, because this way it is giving a more stable ring system, which is a 6-membered cyclic ring, and this can be rearranged into this. So, what we get is this cyclic ring which is 6-membered ring. So, you can compare now the original molecule and the product, where we had started with 5-membered ring and now it is the 6-membered rearranged product that we have formed. Let us now take the case of where double bond participation and rearrangements happen. Properly placed pi electrons of a CC double bond in a substrate can also function as neighboring group and lend the Anchimeric assistance. And this you can see from this particular reaction that the double bond position as compared to this OTS, this double bond will attack on this carbon and help the removal of OTS and give this particular carbocation, and this 3-membered ring and this 3-membered ring and this carbocation, this is a non-classical carbocation which is formed. So, this structure being shown is just one way of representing this intermediate cation. So, this is then further attacked by ACOH, where OAC will get attached in the same position and the same stereochemistry where OTS was there, and the double bond is then brought back in the molecule. So, for this reaction the product has shown the retention of stereochemistry and extremely fast reaction kinetics, that is, this reaction is almost 10⁻11 times faster than that of the saturated substrate. The ability of a carbon-carbon double bond to serve as a neighboring group depends strongly on its electron density. Therefore, when the electron withdrawing CF3 groups are present in the substrate, the solvolysis rate is lowered severely. Aryl groups are suitable neighboring group in substitution reaction. One example has already been mentioned, another example we can discuss as shown here. So, here you can see that how the phenyl group will be helping in Anchimeric assistance. So, this substrate having phenyl here and further this carbon is attached to CH3, another CH3 and the OTS. And when this molecule is reacted with ACOH, we are aiming to replace this OTS with OAC, which is there in the product. It is a perfect retention in the stereochemistry which is there, and if we try to examine this how, it can be understood with the help of its mechanism. And in the mechanism, as you can see here, the phenyl through its double bond is helping in the anchimeric assistance. So, as these pi electrons will be attacking at this particular carbon further attached to OTS, the OTS is lost and we get this 3-membered cyclic ring and this carbocation, and this carbocation via the benzene ring will be delocalized. So, once we get this, then this will be further attacked by OAC minus as shown here. So, OAC minus will attack on the carbon where originally the OTS was there, and then this CC bond leads to cleavage and retention of the aromatic character of the phenyl ring. So, what we get is the product where the OAC has attached to the molecule just on the same side in terms of stereochemistry where the OTS was there. So, what we can say here, there is retention of configuration in the product acetate, and this clearly indicates the participation of phenyl group as the neighboring group. The pi electrons of the ring assist and stabilize the developing positive charge. The intermediates, for the sake of bookkeeping, can be shown as the delocalized phenonium ion. So, let us now summarize what we have learnt in this module. We have learnt that anchimeric assistance is nothing but it is a case of intramolecular catalysis where NGP leads to enhancement of rate of reaction. Anchimeric assistance involves two steps, where first step is radiative binding leading to overall first order kinetics. For the reaction that may go by SN2 mechanism, if anchimeric assistance is involved, the reaction proceeds with retention of configuration and with comparatively faster rate. Various functional groups may participate in NGP like COO minus, COOR, COR, OCOR, the OR, OH, O minus, NH2, NHR, NR2, NHCOR, SH, S minus, SO2PH, I, Br and Cl, and many examples we have already dealt with in this module. Neighboring groups with electron releasing property are more efficient as compared to electron withdrawing. In NGP, the intermediate has a cyclic structure which may lead to normal, rearranged or cyclic product. For neighboring group participation to occur, proper orientation of functional group is a necessary requirement, and we have seen the requirement is best when they are anti to each other, and in terms of conformation they should be axially present. Double bond and phenyl rings can also function as neighboring groups in nucleophilic substitution reaction, and we have considered some examples.